Okay, so now we're going to get into this discussion about limiting reactants. Now, this is important because very often there are some chemical reactions, in fact, I would say most chemical reactions, where in order for the reaction to take place, you need to have an excess amount of one or more particular reactants, right? So basically, when you're starting off with these reactions, you're going to end up with a situation where some of the reactants will be in excess, in other words, more than what is needed compared to one reactant, which would be said to be the limiting reactant. So as stated here, um, many reactions are carried out with one particular reactant which is limited in amount, and the others would be in excess. All right. So the limiting reactant, the one that is limited, will be the one that will be completely used up. And it turns out that that reactant will pretty much determine how much product you would expect to get. All right. Another important point being made here is that a limiting reactant is not necessarily the one that is present in the smallest amount, especially when it comes to the amount measured in grams. All right. So just to explain this whole concept, we're going to use a picnic analogy where somebody is given a task of preparing meals for lunch or picnic or whatever. All right. So according to the equation that you see here, this is the formula that is used to determine a packaged meal, right? So one sandwich and plus two cookies plus one orange would give one packaged meal, all right? So let's say you have at hand 10 sandwiches, 18 cookies, and 12 oranges. The question now becomes, what's the maximum amount of meals we can make out of this combination right here? All right, so let's start off by looking at the 10 sandwiches, right? Now, based on this formula right here, based on this equation, if you're going to start off with 10 sandwiches, that means you're going to need 20 cookies because there's a 2-to-1 ratio between the cookies and the sandwiches, right? So if you start off, hold on, let me get my pen here. So if you start off with um, 10 sandwiches, then according to the equation, you're going to need 20 cookies, right? But we do not have 20 cookies, we have 18 cookies, right? So what that tells us is that we won't be able to use up all the sandwiches because basically we don't have enough cookies um, to use up all 10 sandwiches, all right? Okay, so let's take that out. And let's look at things from the perspective of the oranges. So according to the information given here, we're given 12 oranges, all right? So if we are going to use up all 12 oranges, that means that we're going to need 24 cookies because again, there's a 2-to-1 ratio between the cookies and oranges. But we do not have 24 cookies, we have 18 cookies. So what that tells us is that not all the oranges will be used up because we don't have enough cookies to use up all the oranges. All right, so let me take that out. Now let's look at things from the standpoint of the cookies. So according to the question, we're given 18 cookies. All right, so if we are going to use up all 18 cookies, then according to this equation, we need to use 9 sandwiches and 9 oranges. So this can work because we have actually 10 sandwiches, right? So therefore 9 of the 10 sandwiches will be used up, and we have 12 oranges to begin with, so 9 of the 12 oranges will be used up. So what that tells us is that the cookies would be the limiting item. So let me put here limiting, while the oranges will be in excess, and as well as the sandwiches. So the sandwiches will be in excess, and the oranges will be in excess. All right. So this begs the question: how many packaged meals can we make? Well, since the cookies will be the limiting item, then that determines how many packaged meals we can end up with. And because there's a 2-to-1 ratio between the packaged meal and the cookies, that means that the number of packaged meals, so let me put packaged meals, whoops, uh, meals will be equal to the number of cookies, which is 18 cookies, multiplied by, okay, I don't know why this is acting up, multiplied by one package meal, I'm just going to use PM as an abbreviation, divided by 2 cookies, because that's the ratio between the cookies and the packaged meals. So therefore this will be equal to 9 packaged meals, all right? So basically the maximum number of meals that can be created from the combination of 10 sandwiches, 18 cookies and 12 oranges would be 9 packaged meals. So this is basically how the whole limiting item concept works. Basically the limiting item is the one that is completely used up. All other items will be in excess, which means that the limiting item is the one that determines how much or how many of the packaged meals you expect to get. And the same idea will apply to stoichiometric type problems where you have a situation where you start off with several reactants, one of them is limiting, you have to determine which one it is, and then based on that you can determine how much product you expect to get. So here is an actual chemistry example here, the reaction between ethylene and bromine. Let me write the equation for this reaction. Let me see, where can I fit that? Let me write it here. So the equation is C2H4 plus Br2 to give C2H4 Br2. So that's the equation for the reaction, all right? And this is a straightforward 1-to-1 ratio between the ethylene and the bromine, all right? So in this question, go back to the pointer here. Okay, what's going on here? Okay, so in this question, they gave you 28 grams of ethylene, which is equal to 1.0 moles. And they gave you 128 grams of bromine, which is 0.80 moles, right? Now, obviously, 0.8 moles would be less than 1.0 moles, right? And this is a 1-to-1 mole ratio between these two. So obviously that means that in this particular reaction, given the amounts that we're starting off with, the bromine would be the limiting reactant, right? Because you have 0.8 moles of bromine compared to 1.0 moles of the other reactant, which is ethylene. So what that means is that 0.8 moles of bromine is going to react with 0.8 moles of ethylene, right? And therefore, since you start off with 1.0 moles of ethylene, that means that the moles of ethylene left over would be 0.2 moles, right? And because the bromine is a limiting reactant, then that determines the amount of product you expect to get. And again, because it's 1-to-1 mole ratio between the bromine and the product, that means that the product, the amount that you expect to get would be the same as the amount of bromine that you started off with, which would be 0.8 moles. So we have some questions here being asked. Why is ethylene left over when we started with more bromine than ethylene? Well, the answer lies in the fact that even though the mass of bromine is larger compared to the mass of ethylene, the fact is that the number of moles of ethylene is greater than the moles of bromine. And it's a 1-to-1 mole ratio between those two. So therefore, it is a bromine that would be the limiting reactant based on the molar amount and not on the mass amount, all right? And the next question is asking what mass of ethylene is left over after the reaction is complete. Well, as stated here, it's an easy calculation because it's a 1-to-1 mole ratio between the two. So if the bromine is a limiting reactant and the amount of it is 0.8 moles that reacted, that means that the amount of ethylene that reacted would be the same, 0.8. So 0.8 moles of this will be reacting from the 1.0 moles of the ethylene, which means that the moles of ethylene remaining would be 0.2 moles, right? 1.0 minus 0.8 gives you 0.2 moles, all right? And then based on the fact that the bromine is a limiting reactant, as I said before, the amount of product would be based on that. So therefore the mole of the product, which is 1,2-dibromoethane, will be 0.8 as well, which when converted to grams will be equal to 150 grams, right? So basically this is the amount of the product you expect to get. So basically two things will remain at the end of the reaction: the product and the excess or leftover ethylene. All right? Okay. So when it comes to solving these problems, it's important that you determine which reactant is limited, right? That's a very important thing that you need to determine, because the limiting reactant is what determines how much product you expect to get, all right? So one way to solve this particular situation is to perform a normal stoichiometric calculation of the amount of product obtained, starting with each reactant, and then the reactant that produces the smallest amount of product, that would be the limiting reactant. And we're going to see that in this example, which I'm going to work on in the next video, all right? So until then.